is we're going to do some specific test review stuff. As we go through things, if you want your note card back, if you want to add anything to it, you can grab your note card from the stack right here. If while we're doing review stuff, there's anything you're like, ooh, that's a good idea, let me put that on there. Like, I have an example like that one. So those are here. You're welcome to grab one or grab it and make any updates that you'd like to. If you haven't constructed a note card yet, dude, like, you do a lot worse than just kind of making some notes about what we're doing right now. I'd suggest doing that. Or if you've already made a note card and you haven't turned it in yet and you want to make some additions to it, for sure, go right ahead.
So I was on kayaks. Am I going to have to do the homework quiz?
Yep.
When the issues?
Give me time any day this week.
Okay. Sounds good.
Just let me know.
I will.
Okay.
I'll give you some back.
Nick and Nico, I have your half sheets up here too if you decide you want to make any changes or updates or additions.
Thank you.
Yeah, no problem. Yep. All right. So, right here, what we're looking at was my list of things to do or be able to do for the test. And go through and do some examples of this stuff. What that might look like as a test question, talk about how to do it, run through some examples, all that jazz. Again, you're welcome to write down any and all of this, make a new note card, even if you have made one already, and you decide, oh, I'm just going to like use this stuff that you're doing right now and kind of make some other additional notes as you're talking or whatever, you know, like, I don't care if you want to redo it or add to or whatever you feel like doing, okay? All right. So first thing says you should be able to do find a domain for a rational function. So here's a rational function. How do I find the domain for this guy? So Nick says, you said, great. So we're going to set the denominator equal to 0 and solve. And Nick says to solve that, he says, let's factor it. So we get 2 and -2 as the solutions to that, right? What do I do with those then? Because that's not a domain, right? What is a domain really telling me? Yeah, so it's the set of all x's that give us back a y, right? Now, since a rational function has division, that can give us no answer, right? What kind of division problem gives us no answer? When we divide by 0. That's why we're taking the denominator, setting equal to 0. So all other x's, though, should be no problem for us. So our domain should be all the x's except for 2 and -2. Let's represent that using interval notation. How do we do that using an interval notation? Okay. Close, you forgot something. Nope. Well, 0, 0 is in the domain. Or x equals 0 is in the domain. Yeah, there you go. So again, think about it like as everything other than -2 and +2. So you need the stuff less than 2. That's there. You need the stuff between -2 and 2. That's there. And the stuff bigger than 2, that's the stuff there, right? And I use parentheses the whole way through rather than a bracket. Why? What's the difference between a parenthesis and bracket when I do these interval notations? Great. So parentheses means that number is not included at the end, and a bracket means it is included. Why did I want to make sure I use parentheses here on the 2 and -2? Dudes, those are the things where we divide by 0, right? Those are the x's that mean we're dividing by 0. Those can't be in the domain because there's no answer to that problem. Everybody happy on domain? God bless. Yep, good bless you. One more. Where's the next one? You're good? Okay. There's usually 3. All right. Same rational function here, but this time we're looking for the discontinuities. So there's 2 types of discontinuities, right? What are they called? Vertical asymptotes and removable discontinuities. Let's start with the vertical asymptote. How do I find a vertical asymptote? It's not the top numbers. It's not quite.
Oh, it's like crossing out.
The reduced denominator set equal to 0. So to tell if I can reduce this, what do I have to do? Factor it. How does x squared minus 5x plus 6 factor? That'll multiply to give you positive 5, not positive 6. Remember, it's multiplies and then adds. Negative 2 and negative 3. And then the denominator is still the same, so x minus 2x plus 2. What do you notice now? What can I cancel? The x minus 2's, right? So my vertical asymptote is going to be the reduced denominator set equal to 0. Everybody feel good there? How do I find the removable discontinuity? So the removable discontinuity can only occur if there's reducing, and one of the factors is completely reduced from the denominator. So if I look at my problem, there's no more x minus 2's after I finish the reducing, correct? So that's going to be what I use to find the removable. So I set that equal to 0 and solve. But a removable discontinuity isn't a line like x equals 2. It's a location. So it has a y coordinate to it also. How do I find the y coordinate to go with my removable discontinuity? So I put x equals to 2 in my reduced equation. Questions so far on that? Okay. How about the zeros? How do I find the zeros for the function? Close. Now, you're closer before. Yes, it's the reduced numerator set equal to 0. Okay, so pause here to do a little summary. Domain. Denominator set equal to 0. Everything except for those values. Vertical asymptote. Reduced denominator set equal to 0. Removable discontinuity are the completely crossed off factors from the denominator set equal to 0. And the zeros is the reduced numerator set equal to 0. So again, that might be a nice thing to have written down on your note card, was just to... Yup. Where do you want me to start?
At the beginning.
Okay. Domain. Denominator set equal to 0. Your domain is everything except for those values. Vertical asymptote, reduced denominator set equal to 0. Removable discontinuity, the completely reduced factors from the denominator set equal to 0. The zeros is the reduced numerator set equal to 0. Jacob.
Or is it just...
It's just the reduced denominator. The numerator doesn't matter for the vertical asymptotes. Yes?
Can you say the 0 again?
Reduced numerator set equal to 0. So far, so good. Okay. How do I find the y-intercept? You don't need to factor it. Oh, well, you probably should, but you don't. So what is the y-intercept graphically? Where it crosses the y-axis. Any point on the y-axis has what x-coordinate? 0. So what do? I just plug zeros in for x, right? Now, typically, when you do that, we get a number, but what else could happen? Fraction's still a number. Yeah, the denominator could be 0. What would that mean then? There is no y-intercept. So that can happen, right? If the denominator turns out to be 0, big whoop. Just then there's no y-intercept. So what? That happens. But there's at most 1. Could there be none? Sure. Everybody's cool?
It's always x.
Yes. If it exists, right? Which I assume is what you meant, but you've got to be careful when you say always. And mathematicians are always like, ooh, be careful with always. Let me think if I can come up with some stupid counterexample that's like, okay, well, I wasn't thinking about like that situation. Every other time, though? Yeah, probably. Okay. Okay, next thing it's on my list says you should be able to write the end behaviors for a graph using proper limit notation. So I'd give you a graph, kind of looks maybe something like this. So my first question is going to be, you look at this graph, how many end behaviors do you see? More than 3. There's 6. Why are there 6? Yeah, 1 for each arrow. So I'm going to label them A, B, C, D, E, F. So when I write them, that's how I'm going to label them rather than trying to write them next to the graph because I didn't really leave myself enough space to do that. So limit notation are always going to kind of look like this. We just have to fill in two blanks. One for the x coordinate, and then one for like the y coordinate. Everybody okay? So if I look at the arrow I've labeled A, what x value is that arrow pointing at? Negative infinity. Is everybody okay with how Nick came up with that? What y coordinate is the arrow pointing at for A? Nope. What y coordinate is it pointing at? You see how the line there at A is horizontal? What horizontal line is that arrow following? Y equals -2. What is the y it's pointing to then? -2. Everybody's okay with that? Sure. All right, for B. Again, anytime I start my limit notation, I'm just going to write that part down right away, and then I'm going to figure out what I need to fill in. So looking at arrow labeled B, what x value is that arrow pointing to? What x value is that arrow pointing to? -3, good. And what y value is that arrow pointing to? That arrow's pointing straight up, right? Positive infinity, very good. Now we do have to be a little bit careful because if I look at x equals -3, I have an arrow on each side of the -3. Everybody agree with that? So I need some way to represent that B is on the arrow for B is on the left side of -3. So to do that, I'm going to put a little negative sign in the superscript for -3. That's going to indicate this is the limit or that we're looking at the line x equals -3, but we're looking at the negative side of it, the side where the negatives live, right? The stuff less than -3. Is everybody okay with that? So for C, what is x pointing to? -3, but it's the right side of -3, so we're going to include a plus sign in the superscript. And what y value is arrow C pointing to? Positive infinity, because it's pointing straight up. How's this feeling? I don't think I have one that has 6 on your test, but I wanted to pick an example that had like enough stuff going on so you got a lot of reinforcement here. Because I think when we did limit notations before, we were pretty bad at it. Okay, let's look at D. What x value is this pointing to? 1, I heard. That's correct. Now, and then I need the negative superscript because it's the left side of 1. And what y value is it pointing to then? Negative infinity because it's going straight down. Excellent. Okay, how about E? What's the X approaching? Yep, 1 positive. And then the Y, negative infinity. Great. And then we have one more to do. We just got F left. What is the X approaching for F? Good, positive infinity. You could write just infinity there. I always put the pluses on there to make sure that I'm reminding myself to do the negatives on the negatives. And what is the Y going to? -2. Again, because it's horizontal there, right? So if your line, your arrow is horizontal, it's going to be going to a specific Y value, like a number. If it's vertical, it'll either going to positive infinity if it's vertical up, or negative infinity if it's vertical down. Everybody feels better on doing this? Again, it's not difficult. All you're doing is looking at a picture and describing what you see, but the notation is like, you got to know what to do with it, right? And if you don't know what to do, there's not a lot to do. So doing some example is helpful. All right. So the next one asks you to draw a graph, and then it gives you a bunch of stuff going on. It wants a picture that includes all this stuff going on. So I'm going to pause here a minute if people are writing notes so that they can write down the whole question, because there's a lot to write here. Because we want a graph that represents all of this stuff. So I'm just going to pause a minute and just kind of like jog in place if people are writing down the question. They have a chance to write that down, because it's a lot to write down. Okay, so when I'm doing a question like this, what part do I start with? I would not start with the limits. I would start with the asymptotes. So the first thing that I want to draw in are the vertical and or horizontal asymptotes. I think it maybe goes without saying to make sure that you're drawing the vertical stuff vertical and the horizontal stuff horizontal, but I'll say it because sometimes that gets confused. The next thing I'm going to do is draw in my zeros and or y-intercepts. Now, I wasn't given a y-intercept for this problem, but I'm just plotting points at that. Notice that the points for the zeros and the y-intercept are filled in circles. After that, I'm going to draw in the removable discontinuity. I do have to be a little bit careful with this, because how do I draw a removable discontinuity? I use an open circle there. So I got to make sure I draw an open circle there. Everybody's good so far? So the next thing I'm going to do is I'm going to draw what's happening at the asymptotes. So I'm going to start with the vertical asymptotes. So I'm going to start here at -2. I see on the left side of -2, my graph should be pointing down. And on the right side of -2, my graph should be pointing down. Then I'm going to look at my other asymptote, I notice on the left side of that asymptote, my graph should be pointing up, and on the right side, it should be pointing up. Now that is probably enough for me to figure out the rest. So I know that this has to connect to the 0, and it can't cross the horizontal asymptote. So it has to look like that. And that supports what I'm seeing here, that as I go to negative infinity, it's going to 3. This has to go through this point to the removable and then connect up there. Notice I passed through the horizontal asymptote there. That's okay if it's in the middle. Okay, it can't be at the ends, but it's okay in the middle. And then my last piece, I'm starting up here. Well, I can't cross the horizontal asymptote at the end, so I just follow the horizontal asymptote, and that matches what I'm seeing there. So I'm good. Again, it shouldn't be hard if you know what you're looking for and you approach things in the order, right? Do the asymptotes first, then plot all the points, and then worry about the end behaviors. But use the vertical asymptotes first. Don't worry about the horizontal asymptote piece, because in all reality, if you do this, you've already kind of accounted for that, right? The horizontal asymptote is giving you the same information as that set of end behaviors there. So if you draw on the horizontal asymptote, you don't even have to really worry about those end guys or those ends. They just can be like reinforcement. That feel okay? Again, not too tricky if you know how to look at it the right way. If you look at it the right way, it's pretty easy. But you got to be able to read those end behaviors. You know? All right. Last topic are these solving questions. So there's two types of solving problems we're going to ask about. We're going to ask about solving equations and inequalities. Which one is this? An equation. How do I know it's an equation? It's got an equal sign in it. Okay? To solve a rational equation, the first thing I want to do is I want to factor the denominators. I should probably worry about factoring the numerators if they're factorable, because if I can reduce it all, that helps make the problem simpler. That doesn't happen very often, but it might, and it's worth checking, because if you can do it, woo, that often makes your life a little bit easier. All right. If we look at this one, though, obviously none of the numerators are going to factor. Is everybody clear as to why that's the case? Nobody would try to factor x or x plus 2 or 1, I hope. X squared minus 1, how does that factor? Excellent. X minus 1, x plus 1. How about x squared plus 2x plus 1? X plus 1, x plus 1. Now, that's okay. That's correct. I'm going to think about that, though, as x plus 1 squared. And I'll explain why in a minute when I get to it. And the last one, x plus 1, well, I can't factor that. That's a good way it is. So the technique that I recommend that we use to solve a rational equation was called clearing fractions, right? To do that clearing fractions technique, we're going to multiply both sides of our equation by something so that all the denominators cancel out. That something should be the least common multiple of the denominators. So what is the least common multiple of my denominators? Well, let's start with this. How many distinct factors do I see in my denominators? I see 2 distinct factors, right? I see x minus 1s and I see x plus 1s. 2 distinct factors. So I know each of those two factors must occur in my least common multiple. Now I'm going to ask myself, what is the greatest amount of x minus 1s in any single denominator? How many times does x minus 1 occur in any single denominator? Just once. So that'll be x minus 1 to the first power. What is the most number of times x plus 1 occurs in any single denominator? 2, which is why I wrote it as x plus 1 squared. So there's that. And that'll be my least common multiple. All I need are the distinct factors and the greatest amount that that distinct factor occurs in any single denominator. Everybody's cool so far? Okay. I'm going to distribute that through to the left side and multiply it onto the right side. When I multiply that to the first fraction, I see the x minus 1s are going to cancel, and one of the x plus 1s will cancel. So I'm left with x times x plus 1. Is everybody okay there? When I distribute that to the second fraction, I see the x plus 1 squareds are going to cancel. So I'm left with the x plus 2 and then the x minus 1. And when I do multiply the right-hand side, one of the x plus 1s cancel. So I have 1 times x minus 1, x plus 1. I don't really have to write the 1 there, but I'm going to do it now so you can see the pattern. Everybody so far so good? Notice what I've done is I've transformed this rational equation into a polynomial equation. That we know how to do. To solve this polynomial equation, I'd want to start by multiplying everything out. So I'll distribute the x through and then FOIL out the other pieces. So what type of polynomial equation do I have? It's degree 2, so it's quadratic. To solve a quadratic equation, I will do factoring or the quadratic formula. Either of them require the equation being equal to 0. So I'm going to subtract x squared from both sides and then add 1 to both sides. And then if I combine like terms, I have x squared plus 2x minus 1 equal to 0. Can I factor this? Look carefully. No, it doesn't factor. Nick, what's up? Okay. So, since I can't factor this, what must I do? Quadratic formula, which is a hassle, but, you know, it's not that big of a deal. Yep. You want to drop off your note card on your way out? Perfect. Right here is fine. Thanks, homie. Good luck. Get some pairs or some pars or something. What's up? Yeah, go ahead. All right. So 2 squared is 4, and then 4 times 1 times negative 1 is 4. So 4 plus 4 is 8. I know 8 is 4 times 2, so the square root of 8 is the square root of 4 times the square root of 2. And I can reduce those like that. Oops, shouldn't circle it yet. Because there's one more thing I have to check before I can confirm this as an answer. What do I still have to check? Extraneous solutions. So I need to go back to the very beginning and make sure that this doesn't give me a 0 denominator anywhere. Well, obviously it won't, because my only things that'll give me a 0 denominator are 1 or -1, and that ain't that, so I am finished. If it makes a 0 denominator in the original problem, in which case you just discard that solution and just keep everything that doesn't give you a 0 denominator. If all of your solutions are discarded, then you simply say there's no solution. Feel good?
Do we have to check for extremes?
Anytime you're solving a rational equation. Miriam.
Is this 14.2?
I think this was a 0.2 problem, yes. Yep, I think that's right. Because I think 3 is the inequalities, right? Everything else is 14.1.
Are we not having any questions about the inequalities?
We are. I just had, this is the last thing I have to do. So far, so good. Last example. All right, let's do it. So when solving an inequality, what's the first thing I suggested we do? Yeah, we think about it as the equivalent solving problem. Now, because this is a rational inequality, there's fractions, I have to worry about two things. I have to worry about the discontinuities, and I have to worry about the zeros. Everybody's okay here? What are the discontinuities going to be? And I don't care about removable or vertical asymptote. It doesn't matter to me. I just need the discontinuity. Good. It's anywhere where the denominator becomes 0. Any denominator becomes 0. So it would be 3 and -3. Everybody's good? How do I find the zeros? There could be one. So you thinking there's no zeros because if I try to set the numerator equal to 0, it doesn't have a solution. The problem is that's not a single fraction. So you could make a common denominator, add the two fractions, and then set the numerator equal to 0. Or, bless you, we could just solve this problem the same way we just did previously. I would recommend doing that. So, to clear the fractions, what do I need to multiply both sides of this equation by? X minus 3 times x plus 3. Very good. Bless you again. So I multiply to the first one. The x minus 3's cancel. So I have 2 times x plus 3. And when I multiply to the second equation, the x plus 3's cancel. So I have 4 times x minus 3. And then anything times 0 is still 0. Distribute things through. That's 2x plus 6 minus 4x plus 12. Got to remember, take the negative sign with me. That's negative 2x plus 18 is equal to 0. So I get x is equal to 9. Now that I got all my stuff, I'm going to draw my sign diagram. I'm going to start with the smallest value, that was negative 3. And the next value, 3, and then the last value, 9. and I'll need to pick some test values, something less than -3, so I'll pick -4. Something between -3 and 3, I'll pick 0. Something between 3 and 9, I'll pick 4, and something bigger than 9, I'll pick 10. Now, the catch here is to plug those in to see if those values give me a positive or negative value is kind of a hassle because I never made a common denominator here on my function to make it easy to plug in to see if things are going to be positive or negative. So rather than doing that, which sounds like a hassle to me, what I'm going to do is I'm going to use my calculator. So in the y equals spot, I'm going to type in that left-hand side of my inequality. 2 over x minus 3 minus 4 over x plus 3. And then I'm going to use the y1 command. So I'm going to say vars, yvars, function, y1. And I'll plug into that -4. So I get a positive value there. And then I'll plug in 0. I get a negative value there. And then I'll plug in 4. I get a positive value there. And then I'll plug in 10. I get a negative value there. Is everybody okay with how I use the calculator to do that?
Wait, how did you get those?
I just picked anything that was less than -3, anything between -3 and 3, anything between 3 and 9, and then anything bigger than 9. So it just has to be somewhere in that interval that you're checking. But it doesn't matter. I mean, I could have picked -6.924 instead of -4, but like why? Just picks the easiest, some easy number to check. All right, I'm almost done now. We have 2 more things to do. So we need to decide at -3, +3, and 9, whether those should be filled in or open. The discontinuities are always open. The 0 is going to depend on the type of inequality we have. Because this is an or equal to inequality, the 0 is going to be filled. Now, to come up with our final solution, my inequality is less than. So I want the negative parts of my picture. So -3 to 3, union 9 to positive infinity. Notice that the 9 got a bracket because that's where the filled circle was, as opposed to the -3 and 3 that's got parentheses, because those were both open circles. Because the inequality was an or equal to. The zeros depend on the inequality. The discontinuities are always open. Does that work for you, Emily? Polly?
How do I know the other two that aren't covered?
All discontinuities are open. So anything we get via discontinuity from the denominator set equal to 0, always open. Cool? That's the gist of it. This essentially is what you'll have to be asked to do on your test. Okay? So if you have a good note card put together and you're happy with what you've done, turn it back into the pile. If you're still putting some stuff together, want to run through something else or compare with your buddy, make sure that you got everything on there that they did or vice versa, you're welcome to do that. Hopefully by the end of the class you can drop that back off to me. I'd hate for you to leave without it and forget about it. Otherwise, I am donezo's with you guys.